Hi everyone, I'm Hasegawa from Fujitsu Limited. The title is Improving Predicate Representation in Single Generation by Self-Supervised Learning. Single generation is the task that aims to convert images into informative scene graphs. Scene graphs consist of nodes and edges. Nodes represent objects in images, and edges stand for relationships between two objects. In single generation, the node is called as subject or object, and the edge is called as predicate. One of the biggest challenges of single generation exists in the dataset. The figure is the predicate distribution in Visual Genome, which is the most frequently used dataset in single generation. The figure clearly shows that the distribution is heavily imbalanced. Moreover, abstract categories like on or off rotate in the head categories, and informative categories like painted on or playing exist in the tail categories. We needed to tackle heavily imbalanced class distribution and predict tail categories correctly. Our motivation is to apply self-supervised learning to boost variations of the tail categories through data augmentation. To apply self-supervised learning, like SePiR to single generation, we have to answer two questions. First, what data should be augmented? Second, what kind of data augmentation should be applied? The answer to the first question is the visual features of subject-object pairs. Visual features are the features produced by the object detector. The answer to the second question is to replace visual features with other ones having the same object levels in the figure. The object detector predicts boy level for red visual feature and skateboard level for blue visual feature. By using these levels, corresponding visual features are randomly fetched from external dataset. That is how augmentation is done in the proposed method. Each pair of visual features are passed on to the encoder, and the contrastive loss is calculated between embedding from visual features and augmented visual features. We call this system SePiR, which is self-supervised learning for predicate representation. The overview of SePiR is in the figure. There are three stages. First, visual features are extracted using the pre-trained object detector. Second, the relational encoder is trained using a self-supervised learning technique that I explained in previous slides. Finally, by using the pre-trained relational encoder, we train the classifiers to predict predicates between each subject-object pair. Let's jump into the experimental results. We use Visual Genome as the dataset and conduct three tasks. When it comes to evaluation metrics, we use trade-off curves between recall at 100 and mean recall at 100. In the setting, the curves rotating in the right upper area are better at predicting the tail categories. Except for SGCR's task, our method SePiR is competitive to state-of-the-art supervised scene graph generation methods, even though we did not utilize target predicate levels for running the relational encoder. The next result is similar to the previous one. The difference is the number of annotated datasets while training. The experiment is conducted with the use of limited-level Visual Genome. Obviously, SePiR is superior to state-of-the-art supervised methods. Moreover, as the number of annotated datasets decreases, the gap between SePiR and other methods becomes wider. These facts show that SePiR contributes to acquiring the robust predicate representation even without target predicate levels. That's the end of my presentation. Thank you for listening.